So please. We don't hear you.
And now, is it better?
And now we can hear you.
Okay. So I thank the organizers for inviting me to talk to this conference, so today the previous talks were extremely useful for me because you will see many concepts repeated tonight. So that's good. So my main subject is a connection between Koornwinder theory, and in particular the theory of Koornwinder difference operators, and cluster algebra, quantum cluster algebra, and the use of this connection to prove some interesting conjecture which relates the so-called quantum Q-systems and the theory of Macdonald operators of various types. Okay, so I'll follow the program which I outlined here. I start by some basics on Koornwinder operators and polynomials and how they relate to Macdonald operators. Then after describing eigenvalue equations for these Macdonald operators, I'll describe duality, which allows to relate the Macdonald operators to the corresponding Pierre rules from polynomials, and the interpretation of those Pierre rules as commuting Hamiltonians. So that's where integrability will come in. Then I will go to the main subject of this talk, which is this Whittaker limit, in which you get rid of a t parameter of Macdonald theory by sending it to infinity. And so the Macdonald polynomials are known to become Q Whittaker functions. And the Pierre rules, the claim is that the Pierre rules become relativistic Toda Hamiltonians. Okay. So then I'll use all this setting to attack this question about cluster algebra. So there are cluster algebras basically attached to every classical affinely algebra and twisted as well. So of types, say, A, B, C, D. I'm not covering the exceptional types, but this morning's talk by Yamada actually is extremely close to what I'm going to describe, and was about the E8 type. So I feel better not to cover it right now. So this connection will go through the definition of what I call a time translation in these Macdonald or Koornwinder theories, which have to do with symmetries of the underlying algebra, which is the double affine Whittaker algebra introduced by Cheretnik. And it has an SL2Z symmetry, modular group symmetry. And some generator of this modular group symmetry will be used as time generator, time translation of my models, under which the Pierre rules or Pierre operators will be the Hamiltonians. Okay, and so then I will describe for you the main theorems, which are these Q systems, so the definition of these Q systems. And the theorem is that the Macdonald operators in this Q Whittaker limit obey actually these Q systems, which are basically recursion relations, which are algebraic and which are recursive in this discrete time, which was induced by the action of this SL2Z action. Okay, so then I will describe the proof of these main theorems, which involves some very interesting properties of these Koornwinder theory or Macdonald theories, which have to do with what I call universal solutions, but what we saw already in Numi's talk, which he called asymptotically free solutions or expansions of Koornwinder this time, rather than Macdonald, and also the notion of a Fourier transform. So these two notions are crucial, and they enter the proof in a very explicit way. So I'll try to convince you of that. Okay, so this is the plan. Before that, just a very quick slide on the motivations. So basically, what I'm really interested in here are discrete integrable dynamical systems. Okay, and so a typical example of that is provided by cluster algebras. So you can really think of a cluster algebra as a discrete dynamical system as follows. You have a number of variables in an initial seed, and then you have rules of evolutions of those variables, but they can evolve in many, many different directions. So you imagine a multi-time evolution, right? And each time you apply one of those transformations, which is called a mutation, you change all the variables and you evolve. And so you can think of applying iteratively periodic sequences of such transformations, so periodic sequences of mutations, and that takes you in a particular direction in this huge space of possibilities. And you can ask questions about whether such directions are integrable. So do they have conserved quantities? How many? How to characterize them? And this talk is essentially about answering the question for cluster algebras, which are attached to affine Lie algebras of type ABCD. And as I said, I think the exceptional types should go in the same way. And the relation here is with the theory of Koornwinder Q difference operators. So basically, the structure of this integrable direction in this particular cluster algebras is given by the theory of Koornwinder Q difference operators. Okay, so enough hand waving. Let me just show you what these Koornwinder operators are. So we're talking about difference operators acting on spaces of functions, if you want, polynomials, of n variables, x1 up to xn, right? So I just call x is just a collection x1 up to xn. And here is the basic Koornwinder operator, K1. So this index 1 refers to the degree, if you want. So the notion of degree will be basically how many derivatives do I apply? But instead of derivatives, it's a difference operator. So it's essentially applying shifts to variables, right? So gamma I is just shifting the ith variable by multiplying it by a parameter q to the plus or minus 1. So gamma I to the plus or minus 1. Okay. So everything will be Laurent in this case. That is, we consider functions of the variables and their inverses. And typically, we are going to look at Laurent polynomials. Okay. So now this operator has this shift part. And then there's a whole rational function part here, which involves various parameters. So here you can see 4 parameters A, B, C, and D, which are the Koornwinder parameters. Then Q is involved in the shift, and T appears also as a parameter in here. Okay, so there's all these parameters. So as I said, it acts on functions of n variables, and more importantly, it leaves while invariant symmetric Laurent polynomials invariant. Okay, while invariant just because the underlying while group is that of the C-type root lattice. Okay, so it's essentially permutations of the variables and inversion of the variables. Okay. So now, after this Koornwinder operator, you can look at eigenfunctions, of course, and if you normalize them correctly, like in what we saw in Numi's talk, then you get some monic Laurent polynomials, which are symmetric, okay, and they obey the eigenvalue equation. So to make the eigenvalue look even nicer, it's interesting to shift the definition of a Koornwinder operator, and I call it D instead of K now, and I shift it by this explicit functions of the various parameters, right? And then the eigenvalue equation takes its particularly simple form. So we need a little bit of notation here. So first, there is this parameter sigma, which is related to the 4 parameters A, B, C, D, or their product divided by Q, and you take the square roots. Then, so X are just my collection of variables, but there's a sort of dual collection of variables, S, which are related actually to the indices lambda here, which are partitions, right? via this formula. So you recognize the formula you saw in Naomi's talk, but in Naomi's talk, what you had here was t to the rho, right? T to the rho, q to the lambda. So now we have this extra parameter sigma in front, which is there because of the dependence in A, B, C, D parameters. Okay. And then the eigenvalue itself is the elementary symmetric function, but it's a Weyl invariant elementary symmetric function. So it also has to be invariant under inversion of the variables. So it's just the sum of the variables and their inverses. Okay, so it's the first elementary Weyl invariant elementary symmetric function. Okay, so that's my eigenvalue equation. Okay, so now together with this first order operator, there's a whole collection of commuting operators, which was defined by Van Degen. And the definition is unfortunately a bit technical, so I'm not going to be very long, but there's an explicit formula for those Van Degen operators that commute with the previous guy. And they're essentially made of two pieces. There's, again, a shift piece, right? So now I could call this a shift of order alpha if alpha was the order of this multiset element J1 here. So maybe I could just zoom a bit, right? So we're looking at this thing. And so the order I define by the number of variables that are shifted, basically, right? And here we have a complicated sum over subsets of 1n, which are nested into each other, and then some rational coefficients, which are given by this explicit expression here. So not very exciting, but here you will recognize phi, for instance, of the various variables which are involved in their indices being in these various subsets, nested subsets. Okay, so a complicated expression, but the theorem is that the operators that you construct this way commute with the Koornwinder operator, okay, and they have higher and higher order. Okay. So another set of operators that we are going to use also were introduced by Reins much later, okay? And so the observation of Reins is that there are difference operators. So this time I could call it of order n/2, because you see I have n shifts, one per variable, but they are to the power 1/2 and there are signs, right? So I'm shifting everybody, but by 1/2 of a period, okay? So I can call it order n/2 if you want. And this operator, provided I choose my parameters u and v here in a correct way, are going to map Koornwinder polynomials to other Koornwinder polynomials. So it changes the parameters. It's a map on parameter theory, okay? And if you choose correctly your parameters, by applying two of those maps, you come back to the same theory. So you get another operator which also commutes with my other set, okay? So now we have a very big set of commuting operators. So let me just show how this relates now to Macdonald operators in polynomials. So what I'm talking about here is not the usual Macdonald operators in polynomials, which usually are of type A, right? In Naomi's talk, everything was of type A. So now I'm really interested in the other types. So here I listed the types that we are going to be looking at. So there's BCD affine, and then the twisted types, okay? And so it is known that a certain specialization of the 4 parameters A, B, C, D gives rise to the various, to these various difference operators, which are involved in the corresponding Macdonald theories, okay? So the C-type Macdonald theory, for instance, has these 4 values of parameters. I also listed sigma, right? So sigma was just the sort of defect that you have to put in front of a T row to make things work, right? And then I added one more column here, which I call G star. So there's a duality that we'll see in the next slides, which basically relates theories. And it actually just interchanges B and C. So it's very similar to Langlands duality. Okay, so now the next step was to build up some nice eigenvalue equations for these higher operators. It turns out that the Van Degen operators have kind of ugly or not very nice looking eigenvalues. So we had to come up with suitable linear combinations of those guys, you see, still of the same order alpha, which now I call d alpha rather than d alpha, right? And those linear combinations are such that the eigenvalue equations for the Koornwinder polynomials have nice eigenvalues. So these eigenvalues are just the higher order elementary Weil symmetric functions, right? So it's just like the elementary symmetric functions, but instead of just n variables, it's of the variables and their inverses. Okay, so it's a very simple object, and it has a very nice generating function. Okay, so this organizes in a way the operators, the difference operators, in such a way that their eigenvalues on the Koornwinder polynomials are nice. Okay, so here is the general picture now. So these operators that we just constructed, these linear combinations of Van Degen, I refer to as a curly D, and there's going to be one for each vertex of a finite Dynkin diagram associated to each of those algebras, right? Except that the end vertices here for the type D will not be attached operators of the same type, but operators of the other type, the ones constructed by rings. Okay, and so I indicated all the vertices at which you have to consider Rain's operators rather than Van Degen operator linear combinations. So it's very important that I have these operators and nothing else for what follows. Okay, so and also here on this picture, you will see that I have black vertices and light blue vertices. They correspond to what we will call long labels and short labels, which will behave differently in what follows. Here it's really long roots and short roots, right? But this notion of label will be important. Okay, so now comes the duality. So the duality, we saw it already in the type A. Nomi showed us that a certain ratio of a Macdonald polynomial of type A were in fact symmetric between the degree index and variable index, provided I parameterize the variables in a way similar to the way the spectral variables were parameterized, the SI in terms of Q lambda, right? So the SI in terms of Q lambda would be here, and the X's in terms of Q mu would be here, okay? And so now there's a relation which basically interchanges lambda and mu, right? But at the same time as it interchanges lambda and mu, it changes the parameters into parameter star, and the transformation is here. Okay, so this is called Koornwinder duality. So it's this involution on the parameters, which allows to write this symmetry between lambda and mu in this formula. Okay, so the parameter sigma, which is in front, which changes things slightly, as we saw in our table, is such that its dual is just A, the first parameter. Okay, and so this duality, I recall, upon specialization, via the table I showed before, is going to be this Langlands-like duality, which essentially interchanges B and C and leave all the rest invariant, therefore set dual. Okay, so what are we going to do with this Koornwinder duality? Well, the duality allows to obtain Pierry rules for Koornwinder polynomials almost for free. So with no calculation, we have all the definitions we need to get now what are called Pierry rules. Okay, so what are Pierry rules? Pierry rules are how to describe the effect of multiplying one of those Koornwinder polynomials by some elementary symmetric function. How can I rewrite this as a combination of polynomials? Okay, so that's the Pierry rules. So here we start by giving using this parameterization of a variable x, right? And in particular, when I speak of now a difference operator acting on the variable x, I have to explain how it acts on the variable mu, and this is how it does. Okay, so it's a very simple thing. It's just shifts of mu I by epsilon, epsilon being plus or minus 1. Okay, so now I use this duality formula, and I plug the duality formula in the eigenvalue equation. Okay, so here it is. I just replace my p of this x, which was here, by p times this divided by this. Okay, so I change nothing to my equation, but of course now I have this ratio here, which I can rewrite as that ratio here, in which I have lambda and mu interchanged, and all the parameters change to their stars. So this is this star here. Okay, so on one side, I now have an operator which acts on the mu variable, which now is the index of the polynomial. Okay, and on the right hand side, I do the same thing, and I get the eigenvalue, which is function of the s variable, so lambda, and times the same ratio here. So what I find in the end is that as a function of the variable s, the action of the multiplication by an elementary symmetric function on the Koornwinder polynomial of the dual theory is expressible entirely as a conjugation of a Macdonald operator by this normalization of the polynomials, okay, on the polynomial. So just now I just have to interchange x and s, right? And now that I do that, I get the Pierre rules. Okay, so the Pierre rules are multiplication by an elementary symmetric function is a certain difference operator acting on this guy, and the difference operator acts now on the variable mu rather than x. Okay, so it's dual in this sense. And the explicit expression for this Pierre operator is this conjugation, which we just saw. Okay, so this is really an immediate and sort of trivial consequence of the duality, which was not trivial at all. Okay, so what you get is now, again, a series of commuting difference operators in this variable s, right, these Pierre operators. Okay, and I'm going to call them Hamiltonians, and I'll show you why. And upon specializations, the Pierre rules for the dual algebra are obtained from conjugation of the eigenvalue equations for the algebra, right? So you have to go to the dual algebra to get the Pierre rules that you need in your algebra, right? It's a subtle thing that B and C get interchanged in this process. Okay, so now we do two things. We specialize, so we come down from the Koornwinder level to the Macdonald level, and we take this Q-Whittakers limit. So the Q-Whittakers limit is t going to infinity. So when you take t to infinity, if you remember in Numi's talk, the form of the Macdonald operators, it's not going to change much. The structure remains the same. You just get a little bit less terms in the factors, but essentially the Macdonald operators still look the same. Okay, but now what happens is that the polynomials tend to simpler functions, which are called Q-Whittakers functions. Okay, and these Q-Whittakers functions have a construction completely independently of this, which uses the structure of a Lie algebra, which was done a long time ago by Constant, and their eigenfunctions of Toda Hamiltonians, and in this case of relativistic Toda Hamiltonians as constructed by Ettinger. Okay, so it is licit now to think of the Pierre operators after taking the specialization and this t going to infinity limit as Q Toda Hamiltonians. And the Toda eigenvalue equation is simply the Pierre rule, right? So the Pierre rule, I recall, was certain operator, Pierre operator, acting on the limit now of my polynomial is the effect of multiplication by elementary symmetric function. But now you can think of it differently. You can think of this as being an eigenvalue equation. So this is the eigenvalue. So x is the parameter which tells you which representations you're in, and h is the Hamiltonian, Toda Hamiltonian. Okay, so here is explicit formulas for the various Macdonald operators, which are just the, I mean, I should call them maybe Q-Whittaker operators, right? These are the Q-Whittaker limits of Macdonald operators, t going to infinity, and they look like this. So the first order one, so you recognize it looks very much like the structure of my first Koornwinder operator, but now the coefficients here are rational functions which depend on it on which algebra you're looking at. Okay, so you have formulas like this, completely explicit. On the other hand, out of these formulas, by conjugation with respect to normalizations of the polynomials, you can get Hamiltonians, right, or Pierre rules. And here I'm writing the Pierre rules in terms of the root systems of the various algebras. It's kind of a compact way of thinking of these Hamiltonians. So the first remark is that all these Hamiltonians are actually Laurent polynomials in those variables lambda, which are just the exponentiation of these lambda I, which were the indices of my polynomials. And so we have lambda I, which are just q to the lambda I, and ti, whose effect is the shift of lambda I by q if I act on lambda I by ti, right? So these are just a set of variables which are very handy to describe these Hamiltonians, because these Hamiltonians act on the lambda variable by shifts, right, in one or the other direction. And the coefficients turn out to be not complicated rational functions, but just Laurent polynomials. So this is a drastic simplification that we get because we've taken this limit, this Whittaker limit. So here is the completely explicit expressions of all these Hamiltonians. So let's look at the type C, for instance. So type C, you will recognize various things here, but here what's important is if I compare type C and type B, remember that you get the Hamiltonian as Pierre rule, and that Pierre rule was the coming from the Macdonald operator of the dual theory. So the roots that appear here, this is a root of Bn, and this is a root of Cn. But you see the root of Cn appears in B, and the root of Bn appears in C, right? And the reason for that is this duality we talked about. So all the formulas actually involve the roots of the dual algebra, right? These alpha stars are all the roots of the dual algebra. Okay. So, and here I recall just that these variables lambda and t, lambda is just the exponentiation of small lambda, and t, q commutes with lambda in this way. They form what's called the quantum drops. Okay, so now I come to really the important part of what I want to describe, which relates all this to cluster algebra, because so far there is absolutely no connection. And it has to do with actually the underlying algebraic formulation of the Macdonald operators, but then the Koornwinder operators as well, thanks to some work of Nomi. So there's a famous Nomi representation of the double affine Heike algebra with extra parameters A, B, C, and D, in terms of which you can define in a compact way these Koornwinder operators. Okay, so it all lives in a double affine Heike algebra, which has generators and relations. So I'm going to go very quickly on that. But the important thing is that the Macdonald and Koornwinder theories associate basically elementary symmetric functions of a set of variables y involved in these commutation relations. But Weyl invariant elementary symmetric functions give you directly these operators, okay? And the fact that you chose this particular function of the y's tells you that you get these particular operators, which we engineered in such a way that their eigenvalues would be elementary symmetric functions invariant elementary symmetric functions. Okay, so this is how it works, and rho is just the functional representation. So in the functional representation, acting on functions of x1 up to xn, then these elements of the Daha become our difference operators. Now, in Daha, there is a number of symmetries, but in particular, there is an SL2Z symmetry. Okay, so because the whole thing actually lives on a torus. And so this SL2Z symmetry can be realized in this representation. And in particular, one of the SL2Z generators is given by what Cherednik calls the Gaussian, and for a good reason, because this looks really like a Gaussian. So remember, xi are the variables. Now you're considering the log of xi, and you have to do some sort of Gaussian of the log of xi. Okay, so this gamma operator is very important because it will allow us to define time translation. So by time translation, I mean the following. So first, I take my various operators I described to you. I take the t going to infinity limit after having specialized to Macdonald. Okay, and now I start with these operators, which I have in my hand, and I act on those operators by this generator of SL2Z in the functional representation of Daha. And that's going to shift my operators, right? And that defines for me shifted operators, the alpha n. And there's a caveat here. If you remember, we had this description of vertices of a Dynkin diagram being attached to difference operators, but I had a distinction between long vertices and short vertices, right? Long labels and short labels. And it comes in back here. That is the Macdonald operators corresponding to short vertices will have their time advancing twice as fast as the time of long labels. Okay, so that creates a bit of a mess in how things evolve in time, because certain operators are evolving twice as rapidly as others. Okay. So, and indeed, so the d alpha 0 here, this d alpha is just the Macdonald operator. In the case of long labels, everything's fine. But in the case of short labels, you need to specify both values of epsilon equals 0 and -1. So 0 is also a Macdonald operator, right? The d0 are the Macdonald operators. But the d with -1 index, what time -1 if you want, you have to define them, okay? And so you first define the d1 -1 in a very similar way to which I showed you the d1 0 were defined. And then iteratively, you construct the dA -1 as iterated commutators involving the previous guys. Okay, so it's a bit technical, but you can define all those guys. And then there were the guys circled in green, right, where we use different operators which were based on the range operator, right? So it's actually essentially for the type Bn, but you have to do something very specific. Instead of evolving the range operators with the same time, you're making an operator which is a composite of time 0 and time -1. Okay, and you have to do that to get the correct structure. So by now, I have introduced a deformation of my Macdonald operators by this time variable, which is an integer. Okay. All right. So here come the main theorems. So there are recursion relations in time. So expressing time n+1 in terms of times n and n-1, which are called Q-system relations. Okay. So the first theorem is that the Q-system relations, which are entirely attached to the various algebras, are actually satisfied by this deformation, time deformation of Macdonald operators. And moreover, at time ±1, the operators correspond to what are called raising and lowering operators. That is, they change the index of the polynomial by adding or subtracting a column of A boxes to the partition. Okay, so these operators are actually the generalization, if you want, of the operators constructed by Kirillov and Naomi for type A, in which they had some explicit construction of those raising and lowering operators, and for arbitrary t. And this is at t going to infinity. This is only in the Whittaker limits. So here are the quantum Q systems. So I announced recursion relations for these operators. So here the operators, I call them QAN instead of DAN, because I don't know yet that the ones are the others. But so these are the various systems of the various algebras. So these are quantum recursion relations, right? Because these objects are not commuting, right? And so they actually obey Q commuting relations, which are coded here, in terms of the data of these two finite Dynkin diagram or finite algebras underlying each of those cases. You remember this was G, and I can attach the finite root lattice associated to G, which I call R, and its dual, R star, and these are the fundamental weights of R and R star. Okay, so this matrix is perfectly well defined, and these commutation relations are perfectly well defined as well. And these are the Q systems. So the claim is that the Macdonald operator, these difference operators, they obey all these recursion relations in terms of this time, which was introduced by applying one of the generators of the SL2Z symmetry of the underlying double affine Acre algebra. So two remarks here. The first remark is about cluster algebra. So except for the A2N2, which is always the nasty case, all the Q systems are mutations of a quantum cluster algebra. So cluster algebra is usually defined by a quiver, right? So here I draw for you the quiver of type D. So here, the rule of thumb is that you have to recognize the Dynkin diagram, and then it's doubled. And actually, the way the arrows are distributed is actually according to the Cartan matrix. So there is an adjacency matrix for such a quiver, and it's given by the exchange matrix. And so for the untwisted cases, it's a function of the Cartan matrix in this way. So it's a 2x2 block of matrices. So it has size twice the rank, right? Because the rank would be just one Dynkin diagram, and here we have two. So it's twice the rank. And in the twisted cases, it's slightly different, okay? And in terms of cluster algebra, this one is skew-symmetric, but this one is only skew-symmetrizable, okay? So we have two types of cluster algebras involved, okay? The remark number two is that all this construction of Van Degen operators plus the linear combinations we took in order to have the right eigenvalues are actually equivalent to a quantum Wronskian solution of the this particular set of equations, which are the A-type quantum Q system. And there's a very neat way of understanding how to express QAN in terms of Q1N. You see here you have a sequence of equations. The lowest one is A equals 1, and then it goes up, right? So the eighth solution of the eighth equation can be expressed in terms of solution of the first equation as a determinant, but not quite a determinant, but a Q determinant. So it's actually expressible in terms of Gelfand-Retac quasi-determinants that we heard about in the previous talk. And this relation here, you can interpret as a sort of quantum Denano-Jacobi or quantum Lewis-Carroll or quantum Plucker relation between the minors of a matrix with non-commuting entries, right? So the full determinant here times the minor in which you remove first, last column, first, last row equals this product of two minors minus this other product of two minors. And this index Q means Q determinant. And the Q determinant is actually completely explicit. it's expressed as a sum over alternating sign matrices, which generalize the permutations in a very neat and straightforward way with specific coefficients and specific dependence on the matrix elements. But all this is well defined. Okay, so just to say that these weird linear combinations that we've been considering actually have a very simple meaning once you try to relate the higher order operators to the lower order operators. Okay, so let me come to the proof of my main theorem. So I recall the main theorems are the fact that the operators satisfy the quantum Q systems and the fact that we have these raising and lowering operator conditions. Okay, so the key ingredients are, there are three. There's the notion of universal solutions, the duality, which we saw already, and the Fourier transform. Okay, so the universal solutions, it's exactly what Naomi described, but now we're repeating what he said, but with Koornwinder theory instead of Macdonald. Okay, so we're looking for solutions of the eigenvalue equation, right? But now in the form of series, right? Infinite series with a certain normalization, and which happen to be sums over the positive out lattice or negative out lattice in this case. And if you remember, the condition that Naomi was writing was x1 larger than x2, etc. It's exactly saying that this thing is a product of xi to the minus beta I, and all these quantities are less than 1. Okay, it's the very same condition when you apply it to type K. Okay, so so there's a unique such solution, and we can expand in power series, and we call it universal solution. And I think in the previous talk it was called asymptotically free solution. Okay, now you can repeat the same thing with the Pierre equation, right? So you get a Pierre universal solution as well, right? So of course the two solutions are related, okay? And so here is the theorem. You can actually relate the two series solution by a function of x only, and that function of x is this infinite product, which involves various quantum logarithms. You've seen those also in previous talks, right? And together with that, we can rephrase the duality condition in terms of just these universal solutions. Okay. So interesting thing about those universal solutions is that they reduce to the corresponding Koornwinder polynomials if I reduce the S variable to be related to some partitions. Okay. Now the second ingredient is the Fourier transform. So the Fourier transform is very simple. It's a map from difference operators which are expressed in terms of a quantum torus of variables x and their shifts gamma, and the quantum torus of variables small s and their shifts t. Okay, and it's such that when acting on the universal function, well, f of x is equal to f hat of s. So you transfer the action from x to variable s, and that's the Fourier transform for you. An example, the eigenvalue equation. The eigenvalue equation is telling you that if I act with the operator, I have this eigenvalue. So the eigenvalue, function of s only, is the Fourier transform of the operator, which acts on x only. Okay? So relation between operators and eigenvalues. So back to the proof now. I want to show that my operators satisfy certain relations. So what I do is I'm going to go via the Fourier transform and look at their eigenvalues and show that the eigenvalues, quote unquote, Fourier transform, satisfy the same relations, actually opposite, in the opposite order. Okay. So we start from the eigenvalue equation, which tells you that the Fourier transform of my operators are just the elementary symmetric functions. But as we take t going to infinity, it's just a monomial. So it's a very simple object. And now, what we are going to do is construct a representation of the opposite quantum Q system for the Fourier transforms. Okay, so we start from the commuting relations, which we solved, So we know already what the DA0 are. They're given by this monomial. So we can get the DA1 very easily. And the T's are the shifts with respect to the lambdas. Okay. Then we continue the definition of operators DAN by just using the opposite relations of the quantum Q system that we want to prove as definition. So we have now all these objects in Fourier transform space, right, which we have completely determined. And now we have to make the connection between those objects and the Macdonald operators. So for that, we sort of trivialize the time evolution given by these recursion relations into just one operator, which we call G, the time translation operator, which does the same job as the Gaussian was doing for Macdonald operators, right? But now we are in this Fourier dual picture, okay? So we need two different formulas for the long labels and short labels, right? Then the proof goes on by showing that the Gaussian is actually the Fourier transform of this time shift operator. And then, as a conclusion, we get that the Macdonald operator are the Fourier transform of these operators that we constructed by hand. Okay? And because they are the Fourier transform, they satisfy the opposite relations. Therefore, they satisfy the quantum Q system relations. And in particular, if you take this n equals to plus or minus 1 and look at what you have on the right-hand side, these are going to be exactly my raising and lowering operator conditions. So I'm going very quickly for a few of the steps. So the step 3 was the construction of the time generating operator. So there are explicit formulas involving, again, quantum D-logarithms for the various time generating operators for my algebras. The step 4 was to show that this time generating operator has gamma as Fourier transform. So it goes like this. You have to show first that this time generating operator commutes with the first Hamiltonian or first Pierry operator. Then use the uniqueness of the asymptotically free series solution of Pierry equations to show that when you act with G on this guy, it's still an eigenvector of H1. So by uniqueness, it has to be proportional. So you know that G on P has to be some function of X times P. And then you determine the function of X by just acting on the leading term of this series. And that gives you exactly what G is, and G is the Gaussian. So you get this formula. Okay, a remark here about the Gaussian, which is very important. This formula is a bit bizarre because Xi were generator in this double affine Hecker algebra. So this thing is really not in the double affine Hecker algebra, it's in a completion theorem. But there's a way of constructing an operator which has the same commutation in the quantum torus made of the x's and their shift operators gamma. And it's this double infinite product. So it's again quantum D-logarithms involving x and x inverse. If you want, this is like 2/3 of the Jacobi triple product identity, right? And so this is an identity, in fact. You can really interpret the Gaussian as a sort of theta function. But now, if you group these guys and use the generating function for the Weyl invariant symmetric elementary symmetric function, you immediately realize that these E hats are the eigenvalues of the Pierry operators, right? So they're their Fourier transforms. So the Fourier transform of gamma is actually a generating infinite product involving the Hamiltonians, which were these collection of Pierry operators, which are the quantum Toda Hamiltonians. Okay, so this is really the reason why this guy is the Fourier transform of gamma. Okay, so and the last step, once I have shown that G has a Fourier transform gamma, then to show this is really easy. You have to remember that the Dn were just the conjugate with respect to gamma, and then you act little by little on P, and you end up with a conjugate of G of D hat, which was the eigenvalue of dA, right, on P, which is exactly the other type. Okay, so, and then for short labels, it's a bit trickier, but it uses explicitly this connection with range operator. That's why I have to define it for you. So let me conclude. I presented to you the proof of this Macdonald cluster algebra conjecture, right? So it covers the case A, B, C, D, and twisted. And indeed, I left out the E types just because they are a bit monstrous. But apparently, people are not afraid of attacking this kind of problem. So I have no doubt that one can do the exact same thing for those types. Okay. So another question that arises here is that this is a very small part of the cluster algebra because we've been looking at a specific integrable direction in the cluster algebra in which a sequence of mutations amounts to changing the time n to n+1, right? So, but what about the other cluster variables? Because there's many other clusters and many other cluster variables in the same cluster algebra. They are all expressible as difference operators. And so they must have a meaning, and we don't understand this meaning right now. Okay, so I showed you how to use these three things, the duality, the universal solutions, and the Fourier transform in the proof. So I think this is a very nice package of three properties that you can put together that descend from this theory of Koornwinder operators and that you can really apply in this case. Okay, so what are the next steps? The next steps is to find cluster algebras, not for infinite T, but for finite T. And so we're somewhere along that way in a collaboration with Alex Shapiro and Gus Schrader and Rinat Kedem. But there is still some work. And then the dream would be to go up to Koornwinder theory. So some people think of a Koornwinder theory as a sort of boundary conditions added on top of the double affine Aker algebra. And there are physical systems called totally asymmetric exclusion processes, which have connections to Koornwinder theory and which do exactly that, add some boundary conditions on some problems of particles that go in both directions, etc. Okay. And the last question, which is completely open, is it is known that in the A type, the right algebraic structure corresponding to Macdonald theory, including, of course, these SL2Z action, is the elliptic whole algebra defined by generators and relation. And so it suggests that one should be able to extend this notion of elliptic whole algebra to these other types that we have discussed. So that's all I wanted to discuss. Thank you.
Thank you for the talk. Are there any questions?
Well, please, if I sorry, well, whatever.
Sure.
If I understood correctly, that if you are well, you wrote about this time evolution as an operator T, and you wrote S, and if I understand that S is just your duality, which is
so
here. Well, there are somewhere long ago.
So there is this.
There is this here. There is the letter S, matrix 0, 1, -1, 0.
Yes. Okay. This S. Okay. Now
this S.
So,
this S corresponds to duality, or
no, not at all. So yeah, there are several dualities. So it's quite tricky. But the duality, you see, is not within the Daha. It changes the labels because it uses the dual algebra. So it's more like a map from G to G star, right? That's what the duality does. And this duality allows you to describe in terms of the Macdonald operators of the dual algebra, the Pierre rules of the algebra G. Okay. And so it's not related to this S. Yeah. And
what is this S?
Okay, so that's a good question. So remember that we're taking t to infinity. Okay.
Yeah.
So we are looking at the Whittaker limit. And I believe that in the Whittaker limit, the symmetry, the structure is broken, right? Because the eigenvalues now are much simpler, right? They have this dependence on t, and so t pins one term in the eigenvalues, which is much simpler. And that's why we were able to actually do this. It's because when you go to the Fourier side, which is the eigenvalue side, everything is much simpler, okay? So by doing this, you break the symmetries. And in particular, it's not clear. So this part of the symmetry is still there because it's independent of t. So sending t to infinity is not a problem. But I suspect that maybe not S, but ST, S inverse, or the other t, if you want, is strongly dependent on t.
I see.
So it's sort of destroyed, more or less, in this approach. Yes.
Thank you.
Sorry, Philip, if it is a correctly put question, but when you speak about integrable directions within cluster algebra, from the other point of view, from cluster algebra itself, what does it mean?
Oh, so it's very simple. It's evolutions under which certain quantities are conserved. So you need conserved quantities, right? So you need invariance under mutation. So you apply these sequences of mutations and you have invariance. And the claim here is that these these Toda Hamiltonians are actually the conserved quantities of the cluster algebra in which the D's are the A variables. The Macdonald operators are the A variables of the cluster algebra, and the conserved quantities in this sequence of mutations that we're looking at are the Hamiltonians. So if you want, you can write these Hamiltonians as Laurent polynomials of the A variables of the difference operators. Of course, a Laurent polynomial of difference operators is a bit weird, right? But you can give it a meaning, and as Laurent polynomials of those variables, they're invariant under the evolution, the n evolution, which means that there's a sequence of mutations you can apply, after which you're back to the same value of those invariants.
But you know only particular sequence of mutations, or all sequences,
yes. So the whole
or
thing,
all sequences under which
it's a very special, that's why I call it integrable direction, because inside this big cluster algebra, it's a very special way of mutating, right? You mutate in a very special...
So it just means that you know only some small subgroup of
absolutely.
This cluster group, right?
Absolutely.
Yeah.
So if you look here, for instance, in this example of type D, right? So the mutations on this quiver that are going to be the quantum Q-system mutations are the following. So you do first all the white mutations, and then you do all the black mutations, right? And you repeat that. So whenever you repeat that, you advance all your all the indices, which are called n here and n plus 1 here, by 1. So
okay.
it's a particular direction inside the cluster algebra. But everywhere in the cluster algebra, your cluster variables can be expressed as Laurent polynomials. So in my dual Fourier picture, everybody was Laurent polynomial in those variables lambda and t, right? Which were the variables and the shift with respect to those variables. So you have cousins, if you want, of the Toda Hamiltonians living in this space.
May I ask one question? This is Naomi. And in my understanding, Foundian found two versions of higher order operators. One is what you explained today, and another one corresponds to the Harishchandra image, are Okunkov's interpolation polynomials attached to columns.
Yes.
So your modification of the D operators is related to the other version, or?
I don't think so, but maybe it's just because I wasn't smart enough to work it out. But I don't think so. But you see, it's just a trick to make sure that your eigenvalues are going to be the elementary symmetric functions, because I know that in the dual, the Pierre rules are the elementary symmetric Pierre rules. Right?
I see.
So,
maybe that is more appropriate for the specializations that
yes.
you are looking. Yeah, thanks.
And also, yeah, I wanted to mention, but I didn't, but this universal function for Koornwinder, when you specify S is sigma T to the rho times Q to the lambda, where lambda is a partition, then again you have this the series
ordinary
collapses, right, and becomes a polynomial.
As in the case of A type.
Yeah, as in this other case.
I see. Thank you.
Are there more questions? Okay, if no, then let's send the speaker again.